Welcome, everyone. I am Puzhao. I'm from DHI. I'm very glad to have this chance to make an overview on the supervision platforms, sensors, and also data characteristics, and also the challenges we are facing when applying machine learning in supervision data. So first, supervision. What's supervision? Supervision is it's a very cost-effective way to monitor the vast area of the Earth's surface, and it provides accurate and timely information on the Earth's surface. And it can be used for monitoring environmental changes and also the vegetation dynamics happening around the globe. So you can have maybe one satellite circling around the Earth and have a global view of on the Earth. And you can do the analysis, and especially when it's some serious data, you can detect, identify the changes along time. So it's super cost effective. And in terms of the observation platforms from the ground to space, so we can maybe use some meters to measure at the ground and to measure maybe the spectral, the hyperspectral machines, and also we can also fly a UAV and to have a very close observation on the vegetation, on the building, and airborne, like we can fly aircraft and to take maybe a strip of the area. And the last one is the spaceborne observation, which can have the global view and also provide data at a global scale. And it can be used for various applications. So in terms of special application, like in general, it's close to the object, like the sensor, the distance between the sensor and also the object. If it increases, and then the resolution will decrease. So like from the ground to space, like generally the spectral coverage will increase significantly. So in terms of the observation sensors, like the most common sensors includes optical, radar, and lidar. These three sensors. As we can see, optical sensors, it depends on the sun illumination. If there's no sun illumination, it cannot get imaged by using optical sensors. And it can be easily affected by the cloud or smoke, especially during the active wildfire, right? So when we use a long wavelength like radar, it ranges from 1 millimeter to 1 meter. So it has the capability to penetrate cloud and smoke, and even can penetrate a dense canopy and to interact with unstory vegetations. So the radar has its unique advantages because it can image at day and night at all weathers, and it will not affect by cloud or smoke. And it's a distance-based imaging. It's totally different from optical sensors. Okay, another one is the lidar. Lidar has the capability to sense the world at 3D, especially can measure the height information, like vegetation height or topography. So it's super important for hydrology and also for estimating biomass and the tree structure, especially vertical tree structure, forest structure. So these three main sensors often used or mounted on the Earth observation platforms. And additionally, like radar sensors, it can be at different wavelengths. It uses different wavelengths, like C-band, X-band, C-band, L-band, P-band. So it means that it uses different wavelengths, ranging from 1 millimeter to 1 meter or even more, even longer. So it can interact with different parts of the tree, like can be leaves, small branches, or trunk. So when we estimating the biomass, like what kind of sensor shall we use? When we consider this problem, like we need to consider how images, or especially radar images, were obtained in what's imaging mechanism, right? So please interrupt me if you have any questions. And this is the electromagnetic spectrum often used in the observation, and we can see the visible light is a very narrow spectrum. So that's a spectrum usually used by the camera, especially like our cell phone and also some other like a photograph. And also like we can see the radar and it use the longest wavelength for observation. So it ranges from 1 millimeter to 1 meter, and LiDAR usually it use infrared at 1 micrometer, like pulse. And not Microsoft is multispectral and hyperspectral usually will range from 400 nanometer to 2.5 micrometer. So usually it depends on the number of bands used for sensing the Earth surface. And the spectral resolution. What's the difference between the multispectral and hyperspectral patterns? And we can see that the left figure shows microspectral imagery and hyperspectral images. And we can see more spectral bands along the, yeah, please. Yeah.
What's special about
Sorry?
What's special about the data for LiDAR? Why specifically?
Why do we use this specific wavelengths for observation for the thing? For LiDAR? Yeah, I would say like in the LiDAR at this wavelengths, I think it can penetrate the canopy, the tree canopy. So it can reach to be deeper, especially into the ground. So you have the difference between like the photons, like it can reach some like the ground and also reach the canopy. So you can estimate the time, the difference in travel time, and you have an estimate of on the tree height or some other like building height or something else. Yeah. So like both multispectral data and hyperspectral data are maybe a sampling of the full spectral profile. So we sample at different wavelengths. Like for multispectral, we sample 10 wavelengths, and we have this information here. And hyperspectral data, we sample like 100 or more than 100 wavelengths. So we have more dense observation on the spectral, and we have better estimation on the pixel's spectral profile. So it means the hyperspectral data will provide more or richer spectral information. So we can use it to distinguish different types of data, different types of land cover or land use. So, yes. And here we show example. We can see two images at different spatial resolution. One at 0.3 meter, one at 10 meter. The first one is obtained by Alexa, and the second one is from the Thunder 2, obtained on June 26th this year. So it's quite new or recent imaging on the Copenhagen. So from here, we can see the high resolution image or high spatial resolution images show much more details than the two. Even like if you want to do maybe like individual tree mapping, which data will you use? Definitely you will choose the max-up data because you want to separate individual trees. Usually individual trees maybe it's close to each other, like I don't know, 3 meter per meter apart from each other. So if you want to separate them, you need to use very high resolution images for individual tree counting. And I think you have heard something about this, like in the PhD defense, it also like this individual tree mapping or counting. But like the lower resolution also have its own advantages. Like you only need to process much less pixels. If you don't want like tree counting, you just want to land cover mapping or land use mapping. So it's more efficient, it consumes less energy or less computation power. So when you handle a specific application, you need to consider what kind of battery you want to use, which one is more suitable for this application. And you usually need to consider the spatial and spectral resolution. Another one is the temporal resolution, because like if you want to monitor wildfires, you definitely would like to have maybe daily information on wildfire progress. So you definitely need more maybe high temporal resolution data, like obtained by Moody's, VS, or other like daily images, even if they are at low spatial resolution, but still it provides quite timely information on the status of the wildfire, I think. So how radar interacts with different objects. So first, like for water bodies, the radar signals reaches to the water surface and scattered away from the sensor. So the water bodies usually will appear in dark in sun images. But for buildings, it's a different story. Like usually the dark ones scattering will happen, so it appears in very bright. Oh yeah, sure. Okay, yeah, now it works. Yeah. So it's that once scattering is the building always appears bright inside images. So it's more consistent inside images for the urban areas. And water it always appears in dark. And road is also very flat usually. So it also appears in dark inside images. So there's also two other, like if it's a rock surface, diffuse scattering may happen. And so you have maybe a proportion of the signals will be scattered back to the sensor. And for trees, like the value scatter will be the dominant mechanisms. So it will be usually appear in gray inside images. And how radar responds to a single tree at different wavelengths. This is just a simulation like from Australian pin. And we can see the responses of different wavelengths radar sensors. And first one is X band and C band, and we can see X band and C band, they are more sensitive to leaves and small branches. But L band, it uses much longer wavelengths, like 27 centimeters. So it only interacts with larger branches and stems. And P bands use even longer wavelengths. So you can see it can only interact with the largest parts of the largest branches and also stems. And when you use a much longer wavelengths, like 3 meters or more or longer, so you can only sense the stem itself. So it means when we estimating biomass, so it depends which part we want to add or to count the weight of the carbon in your tray. Leaf, does it include leaves or small branches or just stem? So you need to choose the right sensors and also the data. So here we show two images obtained by the two multispectral sensor and simple one radar data. It's C1, it's 5.6 centimeter wavelengths. So what's the difference? And what can we observe here? Like in the sun images, we can see the urban areas, especially the building areas, it looks very bright. And especially when the bomb gathering happened. And also we can see the wind turbines like in the field. In optical and radar data, and we can use both data individually. We can still count like how many wind turbines are there, right? And also we can see clearly water appears in dark in some images, and in optical images it's in dark blue. And verticals appears in green in optical images, but like gray in some images. So when we do urban detection or urban extraction, which data is more transferable or more useful for building detection or urban extraction? Because like buildings in optical images can be in different colors, like red or green or white. But inside it's always bright. So you have more maybe generic or simple representation of the urban areas, right? So it means this scattering mechanism works everywhere because it's based on physics rules, right? So so that means the real data, when you train model like based on real data, it will be more transferable than optical in urban mapping. So what kind of like characteristics does EO data have? The first one incidentally is multimodality. So the data can be acquired by different sensors. As we mentioned before, it's optical, radar, LiDAR, even sonar data. And also the imaging mechanism, geometries, contents, they are totally different, even the view angle. So it means they were taken at different angles on same object or scenes. So they are the different representations of the same physical ground truth. And also EU data are geolocated, which means each pixel is corresponding to a specific location on Earth surface. So you can easily fuse different modality for a specific applications. Usually different sensors or different data, they have their own unique advantages in different applications, right? Another very important characteristics is temporal, and especially Earth observation time series observation. Because the satellites take images periodically and systematically, and the quality has been well controlled and validated, right? So temporal information is very important, and usually we are especially interested in the changes happening around the globe. We want to identify the changes either in the urban area or in the remote area that people cannot step in. So we need to use some other tools, observation platforms to get information over there. And also, so for example, today we have thousands hundreds of satellites. It's circling around the Earth and taking photos. So which produce a huge amount of observation data. And even also it's at a global scale. You can imagine how large it will be. It's taking images every hour, every day. So you will have super large volume of observation data. It has become the primary source of the big data on Earth. And also, on the other hand, the Earth-spin data, it measures geophysical and biological properties. It has specific meanings, right? So it has specific meaning. We need to when we use this kind of data, we always need to keep in mind that its physical meanings and how we can use these physical meanings or physical constraints when especially when we consider like the synergy of data driving and fixed driving machine learning together. The last one is Earth-spin data. It has plenty of method. It contains information on the orchestration type, cloud cover, and also different view angles. So this information can be very useful, especially for self-supervised learning. So we can predict the order of the images. We can predict the view angle, because the different modality of data, they are different representation of the ground truth. So it can be taken as two views on the same ground. So which can be used when we in self-supervised learning by constructing and maybe optical modality with rhythm modalities. So that's main observation characteristics, like different from optical, different from the natural images, especially in pure vision. So open access of NASA Landsat archives from 1972 to present, which opens a new area, long time series modeling and especially for urban mapping, for vegetation monitoring. So it opens new opportunities, especially for global long-term monitoring of the ecosystem, vegetation, wildfires, a lot of different applications. So Landsat has been extensively used in environmental applications and also climate change research and disaster response. So I think it's the most values, most extensively used sensors so far. And also ESA has released the 22 infrastructure for network, the 21 and 22 data for free, which follows the Landsat open policy. So we can have access to multi-modality data in virtually like at 10-meter resolution in virtually like 10^2 and 10^1, and which has been used for biomass, for vegetation heights estimation. And also it becomes now the main source of multi-modality data in observation areas. Yeah.
Some colleagues working with standard delivery or using greenhouse indices. They often come with the question of this radiometric calibration, how much one can rely on code one sees, right? So I'm wondering if all these new data streams and new products and satellite constellations that they come up, they advertise a lot like this. They focus a lot on the stage level resolution, but I heard that that's a very reliable column.
Yeah.
If one wanted to use, I don't know, planet, SkySat, or greenhouse indices, one should be very cautious as far as what is green and actually thinking the matter of that green. And how do you go about the coloration when there are so many colors, there are so many subjects, and how do you provide comments?
Yeah, you mean the synergy of different sensors, different optic sensors, for example. Yeah, that's a good question. Usually, like we produce products with a single data source, or maybe like the data sources from maybe especially from the same agency, like optical reader, like since 2001, they have been frequently used together for different applications. And in terms of the like commercial satellites and also like the satellites provided by NASA and ESA, so they can be at very different spatial resolution. Especially planets maybe can be the 3-meter resolution, Mach are at 0.3-meter resolution, and also the inside at 10-meter resolution. So I would say it depends on application. Like because privately I worked on Wi-Fi, like so for tick Wi-Fi monitoring, for example, we have been using Modis, VS, and also Center 2 and Center 1 together because we want to have a thin supervision on the Wi-Fi progressions. So usually we are combine them at the decision level, not at the pixel level. That's one choice. Like you can fuse them together on time, but after you have made decision based on a single modality, a single data source, that's one choice. Another one is like planets, they have very high temporal resolution, and but Center 2 or Center 1, they have a low temporal resolution and also less spatial resolution. With the plots, and combine them, that we need to consider, right? Because we already have the very highest temporal and spatial resolution from planets. Why do we need to still to combine the center or the data from lower resolution satellites? That should be considered. And another one is like especially the multimodality fusion. So if we are at the same spatial resolution, it's easier. So you can combine information, use neural networks or some other classifiers. Yeah, but it really depends on what application you want to do. And like there's another like fusion. It's a functioning. So you have only a single very high resolution imageries, maybe from Landsat from planets, but you want to do a special super resolution for Center 2 or Landsat. So you can use that single band to improve the resolution of Landsat altitude. That's another kind of fusion at the pixel space. Yeah, so it depends on the applications. Yeah, sure. Landsat 6. Yeah, I think it maybe it was that like before before it reached its maybe expected lifetime. But I think so. Also, I never see the last thing that in the export. Yeah.
Are they just are they planned with that 10 and 11 and so on? Or?
Yeah. I think there will be, yeah, definitely will continue Landsat, the Landsat series as the last will be open, and like Landsat 10 and 11, I will be continue updating. I think it's very useful and also promising, right? Because currently we already have like more than 50 years of time series for Landsat data. So it's kind of a time machine that we can throw back to 50 years ago and observe the status of the Earth's surface. And we can do long-term analysis, especially when a wildfire happened in 1972, and we want to observe its recovery profile. So we need to look maybe 10 years of Landsat data and its recovery speed and what kind of maybe environmental factors will affect the recovery process. So it's super interesting, and also this is a long-term effect analysis, because some patients after wildfire disturbance, they will never recover. So it's a long-term impacts on the local ecosystem. So commercial satellites also brings new opportunities. So we see this very high resolution real data from SI and Kepler space, and even we can record a very short video. So you can track the speed and direction of the ship moving. And from the Kepler space urban imageries, we can see very high resolution real data that we can estimate the building height very accurately. And even sometimes we can see, based on the commercial satellite, we can see the moving cars on the road. So with this unprecedented spatial type resolution, so some very interesting topics can be investigated. So in summary, so there's urgent needs in converting this huge amount of Earth observation data generated daily and into valuable information, like it can support decision making and action taking. So there has been some advances in producing global products based on the modern satellites. So this paper shows the global surface water products based on Landsat. So it's processed 4.7 billion things from Landsat 5 to 5, 7, and 8. So it produced the global surface dynamics from 1984 to 2021 based on exported data. So it's Landsat plus traditional machine learning approaches. It produces these global surface water products, and it has been widely used in hydrology map, and also the surface value accounting. So currently the deep learning, especially the deep neural network, it has been advancing the education application. So demonstrate it should be able to produce much better results for the global storage water ranking. So it has a good potential to improve the products further and integrate deploy it for long-term applications. And this is a product produced by DLR. It's a reward settlement footprint evolution from 130 meter resolution. So it's a long-term products to map the urban expansion in Dubai and Las Vegas. So we can see these 50-year urban growth, and also it can be associated with the population. So we can estimate the urban areas and the correlation with population. Another one is ESA, SSI initiative. So it produced multi-year global above-ground biomass. So the product is mainly based on the radar data, and for like this year, like from 2010 to 2021, based on feedback into one, or any that depending on the years, because into one is only available from 2015, and also Arrowband 1 and 2. And as we mentioned, Arrowband, it can penetrate deeper into the tree canopy and has more interaction with the aneuploidy vegetation and also the stems. Also, we take the LiDAR measurements from JET and SSL2 and as supervision signals to train them for it, I think. Yeah, it's also the traditional approach that produce the global mass products at 100 meter resolution, which means which can be updated with deep learning based approaches, which can improve the quality of product and also the uncertainty estimation. So the final example is the global company has mapping with the smart leader supervision, and like the bottom column row, it shows the products based on that 30 meter resolution based on regulation tree for regulation. And the second row shows the equals products at each biomass group can be had biomass products, can be had products. Is based on the 2 at 10 meter resolution using deep learning. And a recent one is the second row is the more recent one is based on the fusion of SSL1 and the 2 at 10 meter resolution, also based on the unit. So we can see there are already some advantages like in combining the modern satellite lecture and machine learning approaches or deep learning approaches to map canopy heads based on the LiDAR point cloud supervision. So it's so interesting to see these advances, and yes, and the success of the current models is primarily based on supervised learning from large volume of label data, but it's super expensive to obtain label data for observation data, especially it's serious data. So, and the interest for dense prediction is like this prediction, like you need to have a pixel-wise label. It's super expensive and time-consuming compared to image level labeling. So other hands it's sorry. So it means like label data it may not represent the true distribution in observation data, because label data is just a small portion of the total amount of observation data, right? So it means like how to efficiently use unlabeled data to improve the application in different areas is super important. And also unlabeled data is helpful in identify or to see the whole picture of the distribution in observation areas. So let's go continue with challenges in machine learning for observation data. So we also see some advances in observation data over the years, and we can see the data size is increasing, significantly, especially from the boom of the deep learning. So from the figure, the left figure, we can see the object detection and the semantic segmentation are the two or the most popular two tasks still in observation areas. And we can see some significant increase in the minority tasks due to the boom of the deep learning and in yellow color. So it means some tasks that are not included by other categories. And from the figure below, we can see 60% of the observation data are prepared by satellite platforms. So satellite platform is still the main source of the big data, satellite observation big data. But yeah, we can see it, or we can imagine it will increase further in the future, especially when people are interested in more like global applications, global research. And the middle figure shows the 55% of EU data, it only includes RGB. It means more than half of the that only includes RGB, which didn't use or didn't use observation data more meaningfully, because observation data, the difference between observation data and the camera data is like it includes more spectral bands other than the RGB survey. And only less than 20% are multimodality data. So, and we can foresee there will be a significant increase in the future few years. There will be things that because of the boom of the multi-module deep learning, and so especially the self-supervised learning, it will depend or have more could be more powerful when employed multi-modality classification data. And 80%, around 80% of the EU data are single-term. As we mentioned, the time series of time variable is super important in observation, but currently 80% of this data are single-term based. So when preparing like data, how should we deploy the multi-temporal observation data, and how to use this time series data to benefit the learning of machine learning models. That's super important. And also when we preparing each market for large-scale observation applications, we need to consider a few characteristics or properties, especially when we have the access to multi-platforms. So we would like the data to be more like cross the platform, can be from UAV, airborne, or spaceborne observation systems, and also multi-sensor. So the sensor can be optical, either with film data, and multimodality. It can be point cloud, can be raster, can be vector. A lot of different modalities can be combined together for specific applications. And also the acquisition geometries. The most important, like the data should be geographically well distributed, because we want this data to be a better representation of the real world, the whole world. And we, as we are currently observed, like the living data are mainly available in developed countries, but it's not that many. There are not that much living data in maybe developing countries. So the model may have bias towards developed countries. And so we need to consider when preparing large-scale benchmark data sets, and to make sure they are geographically well distributed and also temporally well distributed, because the seasonal variability may also affect the performance of models. And since observation data can be at very different spatial resolutions, if you want to use this data to be able to do applications at a variety of spatial resolutions, then we should also include different spatial resolutions observation data in the dataset. Another very important is, like, we would like the data to be more diverse in terms of land use, land cover, and climate zones. So in other words, it's also kind of a representation of different ecosystem, different cultural area or geographic areas, and especially like the buildings in Europe or buildings in Asia. It could be very different. So definitely we would like to have the better sample from these two different areas. Another one is the challenges in long-term series modeling and prediction. As we mentioned, like Landsat has 50 years time series data. How shall we use this long-term series data, and how shall we model this long-term series? And there's some basic applications, like based on the DT. It's a continuous gene detection and classification. It's a harmonic-based model. So it first detects the breakpoints, and to cut the full time series into segments. And for each segment, they use a harmonic model to fit the segment. It's kind of use harmonic model to comprise the full time series into a few parameters represented in harmonic models. So it's very simple. Like, it can be, because why does we use this harmonic model? Because it represents the vegetation phonology. So you can use the amplitude phase to denote the vegetation's growth season, and or kind of like it reflects the vegetation's dynamics. So it's simple but effective. It can detect the changes efficiently, and also can do classification consistently, as we can see from the red figure. a case study in land cover classification, and we can see when CCTC features or events were used, we can get a more consistent classification result and higher accuracy across the years. But other features that didn't include CCTC features, it has some ups and downs, and so it's not stable prediction over years. So when we use deep learning or other machine learning, can we learn from this long-term theory? Because this long-term theory, it has intra-year and intra-year variations. How can we model this variation along a long time? Within a year across years, how can we use deep learning or machine learning to model this long-term and make it predictive? Right? Since how we model, it has a temporal embedding, and it can predict or can produce synthetic images at any given time. Right? And another one is when it was observed that like imbalanced utilization rate across modalities in urban mapping. So when one uses radar and optical together for urban mapping, and also observed that the model of the depth fusion model is a kind of a unit with a module that can pass information from optical to radar or radar to optical. So you can choose to turn it on or off, and you can observe the dependency of the final output on one single modality. And it was observed that urban mapping, it depends more on some modality than optical modalities. So why? As we mentioned before, like radar data has a simple representation of the building up area or building areas. But optical, it may contain different colors, different colors, can be different, very different for each bacteria across geographic regions. Because people in Europe may prefer the red roof, but in Asia could be green roof or something. It's hard to transfer between these two geographic regions, right? So it comes, yeah. Yep.
The only objects in urban areas that are right.
Yeah, that could be possible. Like the example image I showed, like the wind turbine in sea, it also has a very strong signal there, but it's not building. But this kind of phenomenon, it's maybe it's less compared to building areas. Building areas is more dominant land covers that have this stop bounce scheduling mechanism. So that's the reason, like when we do large scale area mapping, so it's still like the star modality have a better or more dependencies from the predictions. Yeah, but come back to wildfire again. So when we do for wildfire mapping, the burn areas usually appears in red in optical emitters, but the sun emitters can be very different. It depends on the land cover types, the burn severity, and also a lot of the environmental factors like topographic features. So I assume or I predict. So the burn area mapping or burn area mapping network may depends more on optical device rather than simultaneous. So it's similar, I think, reasons. So which means like, so the challenge is like how to optimally combine the measurements from different sensors or modalities into a generic representation. It means optical and radar, they have some common information. Like shapes, maybe they all capture maybe the building shapes or something. But they still are representing the same object in quite different way. How to optimally combine the information from the different modalities? Do we need to separate the common information from unique information from different modalities? How can we combine the information from them more efficiently, more to get better results? Another challenge may be posed by long-tailed class distribution. As we mentioned, like there are more labels in developed countries or regions than developing countries or regions. So when we train the model might be biased towards developing countries. And also another, it may be biased towards the majority classes, since the rare classes were underrepresented in the data. And another is poor generalization, since the rare classes was not well represented in the training data, so the model would fail to generalize to these rare classes, especially across regions. This figure shows the distribution of the maybe around 300 EU data sets, geographical distribution, and we can see, yeah, USA has the largest number of EU data sets, and so we can see a clear long-tailed distribution also in its geographical distribution figure. And another challenge can be the synergy of the data and physics-driven models. Since the physics models, it describes some well-understood phenomena or relationships. So maybe you can use an equation to represent these physical processes. And like physical model, it exists for many areas, like physical, geophysical, chemical, biological processes. They can be represented, or some processes can be represented in with physical models. And data models, it's usually like it works, or it was usually often used for modeling some poorly understood procedure or mappings. We don't know how A produce B, so we just make a mapping function. We learn a mapping function by fitting the data, the input data, and the labels we have in hand. So how can we use those or combine, integrate data-driven, data and physics-driven model together to get maybe a hybrid model that can learn models that fit the physical rules and also represent, it can learn some unknown procedure of physics rules hidden in observation data. So by using this hybrid model, so we can have more consistent and explainable output or prediction, and it's more explainable. And definitely, when we use this model and some training data also can be produced or used, we have more constraints when learning machine learning models or deep learning models. So maybe a live training data is required for the learning of the hybrid models, and is more immune to overfitting. And some other open challenges, like currently the new released observation dataset is usually lacks of diversity, and many of the early datasets they are limited in spatial temporal distribution, and some people has tried to increase diversity from the scene content and environmental factors, and also image acquisition status or processing status. And also, when we prepare a benchmark datasets, and also we need to consider how to reduce the bias evaluation effects, and to also avoid information leakage from training set to testing set because of the spatial correlation. And another one is usually it's not feasible to have the same increase in the labels as observation data, since the data is increasing significantly every day and required at a high speed, but labels usually is more static, and generating labels it takes much more efforts. So also in the observation areas, like we have a lot of low resolution labels available for use, like the labels produced or land covers produced by from Moody's surveyors. So, but we have other satellite data available, like 10-meter Moody's product or labels at 700 meters. There's misalignment in spatial resolution. How could we use these lower labels to train machine learning models together with some unlabeled data? And also it can be treated as a label noise, since they are at different spatial resolution. And also the label noise effects on the evaluation is not well understood and often ignored correctly. As mentioned, the label, also the distribution of labels will lead to the more bias for the developed countries. So we need to consider these challenges when preparing websites, in particular for large-scale applications. And finally, recently we got some very new progresses in producing global country health mapping at 1 meter by Meta. So it used the teacher-student model to learn from unlabeled data, and then fine-tune the decoder using arable data, and then calibrate it with the GA-based prediction. So it based on the maximum better. It has super high resolution, like 1 meter resolution tree can be had. It's interesting, and also it produces very good results. But there's some artifacts available still, like a lot of artifacts, and the special consistency is not as good as Nico's product, right? And so I think this could be solved soon. And self-supervised learning may have the potential to mitigate the shortcomings of the supervised learning by learning with task agnostic representations from other data with self-supervision objectives, like the reconstruction and info better predict self-created label of constructing semantically similar inputs from, for example, optical or radar. They should have similar predictions, but they also contains their own unique information. How shall we balance this similarity and dissimilarity? Right. And okay, by using self-supervised learning, so human annotation maybe is not that necessary for training, and small amount of data could be sufficient for training good performance models. And also we will preparing pre-training data and label data. We can go through the learning gap between these two stages. So the downstream task performance can be ensured. Yeah, I think that's all. Thank you very much. So I'm looking forward to see the new progresses in using self-supervised learning in further education later, in especially large field or even global applications like hydrology, vegetation, urban, everything, environmental monitoring. Thank you very much for attending.